So here in northern Somerset County, it's just before 6 p.m. Eastern, and this is, I think, probably one of the last bouts of snow from this storm. So just to recap on this storm actually produced some pretty decent totals in northern Jersey, northern Pennsylvania, as well as the Catskills. Catskills, we don't have storm totals yet because it's still going on there, but I'm pretty sure up at the tops of the mountains, well over 1.5 feet, maybe approaching 2 feet probably. Even in New Jersey, at High Point, we had a very impressive snowfall total of 20 inches as of 8:30 this morning, and by now it's probably maybe 22, 23 storm total. So quite a bit. Same thing in Pocono Plateau, we got around 19 and a half inches for the highest totals up there. So yeah, definitely an impressive storm. And these higher than anticipated totals were a result of the slowed motion of the low pressure and the stronger low pressure of it, because the stronger pressure led to the storm itself moving slower because it had more resistance to the upper level low. So this resulted in heavier snow over the areas where it did snow for much longer. For example, in Brookside, New Jersey, which is just north of what the rain snow line of this system used to set up to be, 5 inches. And where I am, which is just south of where the rain snow line set up, is 0 inches. It was just raining the whole night. So yeah, another important thing I want to talk about is the southern extent of the precipitation shield in this system. It was cold enough for snow. Like where I was, it was 37, 36 around the whole night, yet it was raining. However, areas further north, it was 36, 35, and it snowed 5 inches up there. And the reasoning for this is because with the cutoff is basically where the cutoff of the rain snow is. It's just because of the precipitation, right? The precipitation is lighter in that area. And I wanted to mention two things here, both latent cooling and dynamic cooling. So when you have lighter precipitation falling in marginal temperatures like 35, 36, 37, right? When you have light precipitation falling, it ends up falling as rain. And when you have heavier precipitation falling, it ends up falling as snow. Now the two reasons, first one, latent cooling. So when you have a lot of snowflakes falling through the air, even if temperatures are like 3-4 degrees above freezing, not even 3-4, maybe even 5 degrees above freezing, what happens is the amount of snowflakes that are there, right? They're able to absorb the heat more equally. The amount of heat in the air that is warmer is able to be absorbed by many more snowflakes, if that makes sense. So they're trying to equalize out temperature, the air and the snowflakes, but there's so many more snowflakes that each snowflake only absorbs a little bit more heat. So they don't really melt on their way down. But when you have really light precipitation, there's a lot less snowflakes. So they absorb a lot more heat, and most of the time they end up melting. So that's one reason. Now the second reason I want to talk about is dynamic cooling. So when you have strong upward motion, right, like these snow bands, for example, when you have stronger upward motion, as the air rises, as we go up in height in the atmosphere, temperature decreases, right? So the air that's starting at the surface is at a different pressure, right? Actually, I meant to say pressure decreases before, not temperature. Temperature does decrease, but what I'm going here is pressure. So as the air at the surface rises up, it needs to drop in pressure to equalize, right? With the air above, because we're trying to get equilibrium here, right? So as our air rises, it's going to expand to reduce its pressure, right? And this is an adiabatic process, right? There's no exchange of heat in the atmosphere. So what it's going to do is, as it rises, when it expands, it's going to use its own internal energy to expand. And this results in the temperature dropping, since we're using up some of that energy to expand. So the temperature drops. And this drop in temperature results in cooling of the air column, which in turn makes it colder, both at the surface and through the column, allowing for snow to be more seen towards the surface and accumulate as it comes to the ground rather than melting. And in lighter precipitation, you don't have this dynamic cooling. So it usually, again, melts before it reaches the ground. So the reason it's snowing right now over here in northern Somerset County is because the temperatures have dropped around 34, 33 degrees. And it's actually starting to stick. If you look on the ground and the snow over here, on the grass over here, it's starting to stick, as well as on elevated surfaces like this box over here. So I think, though, this is going to be one of the last bouts of the storm, so nothing significant. Basically a trace, maybe at best half an inch of snow if this continues for any longer. Not sure how much longer this is going to continue for, though. But yeah. So I hope you guys understood why areas just south of the rain snow line didn't really see much snow, whereas areas just north of it saw quite a bit of snow. Because honestly, I was quite frustrated that we didn't get much snow here. I'm sure many other people were as well. But anyhow, I guess the reason to explain that is just the science of the atmosphere. Hope you guys learned some about latent cooling and dynamic cooling. And yeah, I hope you enjoy the snow if it's snowing where you are. And yeah, keep an eye out for that storm that could happen on Thanksgiving. We're still looking out for that. It's still not really sure whether it's going to be a rain or a snowstorm. It's definitely not looking like it's going to be as cold as it was before, but still something to watch. All right, thank you guys for watching. Hope you learned something.